Good day. I hope we're all feeling and doing fine today. In this discussion video, we will be looking at some examples of line integrals, which are solved using two important concepts: the fundamental theorem of line integrals and independence of path. So let's look at those two concepts first. We look at the fundamental theorem of line integrals, which needs the following: a piecewise smooth curve C that is parameterized by a vector valued function R of t, where t is between a and b. We also need a scalar function phi whose gradient f, so here f is the gradient of phi, is continuous on some region containing C. Then the FTLI provides a useful shortcut in computing the line integral along C of f dot dr, and we do it as follows. First, we evaluate phi at the terminal point, R of b, and subtract the value of phi at the initial point, R of a. So that's the first thing we need. Another will be this one, the concept of independence of path. Here we have a vector field f whose component functions are continuous on an open connected region B. Then the following statements are equivalent. All right, we know how to check if a vector field is conservative. We will be reviewing that in a while. So if we prove that f is conservative, then the line integral of f dot dr along any curve C will be the same, regardless of the path C connecting the initial point A and a terminal point B lying in the region B. Okay? In particular, if A and B, points A and B coincide, then the curve C is closed, making the line integral of f dot dr equal to 0. Okay? Those concepts will be needed in solving these exercises. These are the first four that we have. Feel free to pause the video if you want to try and solve these items first. On my part, I'll pause for 10 seconds. Okay, those are the first four. We have 3 more over here. Again, feel free to pause the video and take a look and try these items if you wish. Okay, so let's try these exercises, shall we? We have this first item here, where our task is to evaluate the line integral after proving that it is independent of path. So here, we have to show that this is independent of path, where C is any path from the point 1, 2 to the point -1, 1. Okay? Here, C is just any path, so maybe it hints at some independence of path, no? All right, which, according to the 3 statements earlier, would hint at a conservative vector field being involved here. So let's set up that vector field first by writing the 2 components PQ of this vector valued function f. So we have P equal to the first component, 2xe to the x squared minus 2y, and Q equal to 2y minus 2x. Here we check if your vector field PQ is conservative, and in the 2 variable case, we can do that by checking if Q sub x, the derivative of Q with respect to x, is equal to the derivative of P with respect to y. Let's do that. We start with P sub y, which is the derivative of 2xe to the x squared minus 2y with respect to y. And that will be equal to 0 minus 2. On the other hand, we have Q sub x, derivative of 2y minus 2x with respect to x, and that will be equal to 0 minus 2. Okay, so that's what we want. Q sub x equals P sub y. giving the conclusion that your vector field PQ is conservative, making the line integral given here independent of path. So that will enable us to evaluate this integral using FTLI. Okay? To that end, we will need a potential function. So let's take a look again at how we recover the potential function phi for f, which is PQ. All right. Again, since f is the gradient of phi, then the components of gradient phi must match with the components of f over here. That would give rise to two equations. First, phi sub x is equal to the first component p, like this, and phi sub y will be equal to the second component. Okay. So those are the two equations that we will need to solve for phi. Let's start with the first one. We solve in terms of phi sub x first. We integrate now with respect to x to get your phi of xy supposedly. That will be the integral of p dx, keeping y constant. So we do this term by term. We have e to the x squared minus 2xy plus a function of y. Again, y is constant, so it will be derivative 0 with respect to x. So that's why we have g of y, not necessarily a number. Okay? At the worst case, it should be a function of y lang. Okay? Now, we determine what g of y is by differentiating this phi with respect to y, and then comparing it with the phi of y, or phi sub y, from the equation over here. So we have phi sub y equal to, well, e to the x squared goes away. It becomes 0, and we are left with minus 2x plus g prime of y, which is equal to 2y minus 2x. Okay, we cancel that minus 2x there, so we get g prime equal to 2y, and taking the antiderivative gives us g of y equal to y squared plus some real number k. Okay, and that will now allow us to write the final form of your phi of xy by plugging in this expression over here. So that gives us e to the x squared minus 2xy plus y squared plus k. Okay. So we will be using this one in evaluating the integral later by FTLI. So we have the line integral given here equal now to the evaluation of phi at the terminal point, negative 1, 1, minus phi of the initial point, 1, 2. For reference, we put phi here. All right, so the rest now is just plugging in and solving for the values. At x equals negative 1 and y is 1, we have e to the 1 minus negative 2 plus 1. And then at 1, 2, we have e to the 1 minus 4 plus 4. And we just simplify that last line to get the value of the line integral here, 3. So the line integral given here, where c is any path between these 2 points, has value 3. Okay? All right, that's item 1A, which had 2 variables. No? For the next item, we will be doing the 3 variable case. Okay? So we have this line integral of e to the y dx plus x e to the y dy plus z plus 1 times e to the z dz, which we want to evaluate over this specified path. Okay? So let's expand what we did in 1A by introducing a vector field of 3 components, namely e to the y, x e to the y, z plus 1 times e to the z, as p, q, and r respectively. So now we have a check, no? to see if PQR is a conservative vector field, and that is by way of the curl. Remember, we have the curl of a vector field of 3 components to be computed as the del operator, partial x, partial y, partial z, as a vector, cross PQR, whatever PQR would be. I will be leaving it to the viewer to check that this here will be the 0 vector. Okay. And look now, curl F is the 0 vector, and that is another way of saying that your vector field is conservative. Another way of saying it will be the line integral corresponding to F dot dr will be independent of path. Okay. So now we can apply your FTLI again to find the potential function for this vector field, and we can use the conclusion of the FTLI. Okay. But this time, if phi is a potential function for f, then we have 3 equations now, since we have 3 variables. No? We have phi sub x first equal to e to the y for p. Phi sub y is the second component, q, and phi sub z is the third component. Okay. So now we find phi from these 3. Excuse me. Let's solve first for phi from phi sub x, which is the integral. So phi is the integral of phi sub x dx. So that will give us x e to the y plus, this time it's a function now of y and z for the constant, quote unquote, no? Since this part will be constant with respect to x. Okay. All right, so that's the first thing that we want. Now we differentiate this with respect to y and compare it with phi sub y as given here. That gives us phi sub y equal to x e to the y plus g sub y. But we want this to be equal to x e to the y from the given. Okay. So now, well, they both have x e to the y, both sides. So this tells us that g of y and z is a constant with respect to y. So what sort of function would g be? The answer is, it would only have to contain z terms. So g of y, z here must be a function of z lang, which is now reflected in the current form of phi. So plugging h of z here gives us this one. So phi is x e to the y plus some terms involving z. Now to find out what they are, we will be looking at phi sub z from this by differentiating this one with respect to z and then comparing it with phi sub z over here. Okay, let's do that. Phi sub z, well, x e to the y on one hand will go away. So we'll just have h prime of z. And on the other hand, we have z plus 1 times e to the z. Okay. Now, again, I will be leaving it to you to verify that the integral of this expression is z e to the z plus some real number k. Okay. So that now will be your final element for the potential function phi. So that's phi of x, y, z. I forgot the inputs here, but that's x e to the y plus z e to the z plus k. Okay. We will now be using that to evaluate your line integral. But we need the endpoints of your curve. So let's find them out. The curve C here is traced from, when t is 0, it gives us 1, 1, 1. And when t is 1, it will give us 0, 0, 0. Okay. So initial point is 1, 1, 1. Terminal point is the origin. Now, using our FTLI, we can evaluate this line integral as the value of phi of 0, 0, 0 minus phi of 1, 1, 1. Okay. And the rest is just algebra now. When everything is 0, including the constant k, we set this to be 0 for easier computation. Then we have 0 plus 0. And then at 1, 1, 1, we have 1 times e plus 1 times e, like this. So we have the final answer for the line integral here. Its value is negative 2e. Okay, so that's item 1. All right, so far, we have been dealing with examples of line integrals wherein we need to solve for the potential function. Huh? So we have the first 2 examples like that. For the next pair of examples, we have this instruction. Solve the line integral without the potential function. Okay. I think this was done in the previous lecture video on this topic, wherein it was noted that some vector fields might have nice looking potential functions that might be difficult to obtain. That's why we will have to do this a different way. No? So let's try item 2a right here, where we have f to be this one, and c is this nice looking r of t. Yeah. So now we evaluate the line integral without a potential function. All right. First, before we evaluate anything, let's just check if f is conservative para may sense yung susunod na gagawin natin. So we have f as pq. So let's check if p sub y is equal to q sub x for a function of 2 variables. No? Let's try the derivative with respect to y of y squared plus 2xy. That's going to be 2y plus 2x. And for the derivative of 2xy plus x squared with respect to x, okay, pareho lang, no? That's 2x plus 2y. All right. Since that's the case, then it will be the case that f is conservative, making your line integral independent of path. Okay, so there's your phrase, independent of path. Kailangan natin yan. Because again, we got rid of the potential function. Huh? All right. Next thing we want to do is to take note the endpoints of C. When t is negative 1, the initial point will be 1 and log 3 of 1, that's 0. Now when t is equal to 1, that will be cosine of 0, that's 1, log 3 of 3, that's 1. Okay? So now, if we cannot use a potential function, then we will have to fall back to the definition, right? The integral of f of r dot r prime. But if we use the r here, yeah, it looks nice, huh? So we don't do that. Instead, we will be taking a simpler path, a different path, no? Connecting 1, 0 and 1, 1, such that it's f of r dot r prime is a whole lot simpler, okay? For example, well, we can take this. We can take the straight line from 1, 0 to 1, 1, which can be parameterized as follows. So we have 1 comma t, where t here ranges from 0 to 1, okay? So we have r of t here with its corresponding derivative, 0, 1. Okay? So ang mangyayari dito, since we have independence of path, this line integral here will be the same if we consider the line integral along C1. Okay? So that line integral along C1 will be reflected as follows. It's expanded to be the integral from 0 to 1 of f of r of t. So we replace x's here by t. All x's will be 1, rather. Sorry, x will be replaced by 1, and y will be replaced by t. When we do that, we get the following. T squared plus 2t and 2t plus 1. And then take its dot product with r prime. Sorry. So there. And then the rest will be hopefully easy for us. That will be the integral of 2t plus 1 dt with antiderivative t squared plus t from 1 to 0. And at t equals 1, we have 1 plus 1. At t equals 0, we get 0. So now the line integral of f dot dr along C has value 2, which is again obtained using a different path connecting 1, 0 and 1, 1. That other path is justified by the fact that the line integral is independent of path. Okay? So that's a 2-variable example. Let's try a 3-variable example. Okay. For this one, we note that C is a union of 2 curves, a line segment from the origin to 1, 1, 0, and this curve here, with the vector field F being this one. No? So again, we want to solve this without the potential function. All right, how do we do that? Again, I will be leaving it to you to check that the vector field PQR is conservative, meaning the curl of F, which is the del operator cross PQR, is going to be 0. 0 and 0. Vector. So that's the 0 vector for the curl of F, making our vector field conservative so that your line integral is independent of path. Okay? Again, we will be using that fact here. All right. Let's just note the endpoints of C, which again starts from C1 over here. So it starts from the origin to 1, 1, 0. Now let's check where C2 starts and ends. C2, when t is 0, will be located at 1, 1, 0. So it starts where C1 ends. No? And C2 ends when t is 1 at the point 0, 2, 0. Okay? So that's your endpoint. So that makes your curve C, C1 union C2 as defined, starts at 0, 0, 0 and end at 0, 2, 0. Since those endpoints are distinct, then our curve C is actually not closed. So we cannot use the third statement, which says that the line integral is automatically 0. Okay. However, just like what we did in item 2A, we can consider a simpler path from the start point of 0, 0, 0 and end point 0, 2, 0. What would that path be? Let's take this one. First and third components 0. Only the second component will range from 0 to 2. So that's 0t0 with derivative that 0, 1, 0. Okay, so from that, we can use the expanded version again, no? Of the line integral, which starts with this one first, line integral along C muna. And since we noted that this is independent of path, then we can replace C by C3. Okay, which is now equivalent to this one, f of R3. So we replace x's by 0, y's by t, z's by 0, and then we they take its dot product with 0, 1, 0. Okay, game. So we have integral from 0 to 2 ngayon, yung sa t. And then, this f of r3, paki-verify po, yan siya, 0t1. And then we take its dot product with 0, 1, 0. Okay. And then the rest, hopefully, will be easy for us now. That will be the integral from 0 to 2 of t, antiderivative t squared over 2, and evaluation giving our final answer 2. So the line integral of c or of f dot dr along c, which we simplified to the line integral along c3, this c3 here, has value 2. All right? So that's for the first set of exercises that we have. Okay, let's take a breather. And after a few moments, we'll start with the second set here. Okay na, game. Let's deal with these last 3 examples, which ask us to compute work done. Work done. I think we've encountered this before. Let's recall what we do to compute the work done by moving a particle through a force field F, which is a vector field, along a curve C, which is piecewise smooth. No? That will be exactly your line integral here. So work done is line integral of f dot dr. Okay? So let's deal with this example here. We have this vector field F exerting work on a particle moving along this curve. All right. I will leave it now to the viewer to verify a few things. For example, that the vector field given here is conservative. That's py equals qx. That's your parang check. No? And next, we verify now, since conservative yan, line integral natin will be independent of path. Okay? So now, we can either use FPLI or come up with a simpler path connecting the endpoints of R of t here. Okay. For this one, we will be using a potential function. Okay. Paki-verify po, ito ang potential function. Okay. So now, we note that we have to plug in here the terminal point of R and the initial point of R. Okay. When t is 0, R of 0 is 0, 0. And when t is equal to 1, then R of 1 is 1 pi over 2. Okay. So we use these two endpoints now to compute your line integral using FPLI. So we have your work done there equal to phi of 1 comma pi over 2 minus phi of 0 comma 0. Spoiler, when x is 0 and y is 0, this thing will just be 0, taking k to be 0. Huh? So we just take phi of 1 comma pi over 2 with that value e minus 3 pi over 2. Okay. So that's example 3. Okay. All right, let's do another one. All right. We have this vector field F exerting work along this curve here. We want to know how much work is done by F along the curve, okay? Once again, I will be asking you to verify that the given vector field is conservative. But this time, we will not be going along the path of, the path of taking a potential function, okay? Because, yeah, I think you will agree when I say it's quite tedious for this one. No? Instead, we will be focusing on a different property of F, okay? Namely, that the components P and Q are continuous on R squared, right? It's a combination of polynomials and exponentials. So the vector field itself is continuous on R squared. Okay. Yeah, where will that lead us? Well, it will lead us here. We will have to check first, no, the endpoints of R of P. So now we note that R of 0 is 0, 0. Now, if we consider R of 1, it will also be 0, 0. Okay. So we have a curve with initial and terminal points coinciding. So we have a closed path. Okay, so now notice where we are headed, no? A vector field exerting work along a closed path. By the way, the vector field is conservative, no? So by the third statement in the 3 equivalent statements we considered earlier, the work done is 0, right? Conservative vector field on a closed path, work done is 0. Automatic yon. We don't need to compute for the potential function of your vector field, okay? Although, of course, it's a good exercise to figure out what the vector or what potential function will give your capital F here, okay? That's item 4. Item 5, last, okay. We will just show 2 possible solutions to this one, encapsulating yung mga ginawa natin for the past 6 items. No? So we have F here. I forgot F of XYZ. It's F of XYZ. Exerting work along this curve. So we want to find the work done by F along C. The first solution that we will be considering will come from the following observations. Paki-verify na lang po ito. First, F is continuous on all of R3 except the origin. Next is F is conservative by way of the curl. Yeah, paki-check na lang po. Okay? Next, we have a potential function of this form. Okay? This one, I believe this is not tedious at all. So, paki-verify na lang po. And the fourth thing that we need is the endpoints of your curve C, which are 301 and 101. Okay? Okay. So, saan manggagaling yung first solution natin? Well, it will come from the third and the fourth observations here. Okay? So we will be using the fundamental theorem here. Okay? We have the work done equal to this line integral, which by FPLI is equal to phi of the terminal point 101 minus phi of the initial point 301. And when we evaluate that, it will be equal to 1/2 ln2 minus 1/2 ln10, which we could simplify using properties of ln as follows. So the line integral of f along C is equal to this. Okay. Now, that's the first solution. No? What about the second solution? For this one, we will use the fact that f, or rather C, is traced from 301 to 101. So ito parang kanina, no? Yung walang potential function na gagamitin, no? Moreover, we will have to note again that your curl f is zero vector. So that f is conservative, meaning the line integral representing the work done is independent of path. Ayan. So, ang gagawin natin, kukuha tayo ng isang path from 301 to 101 such that madaling mag-apply ng definition. Because again, we don't have the potential function. Okay? Basically, we ignored item 3 from earlier, no? All right. So we will take this following path. Ting, 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 math 22. Pakibalikan po. So we have this curve C1 parameterized as 3 plus 1 minus 3 times t. So 1 minus 3, terminal minus initial. And then 0 and then 1. Fixed yung second and third components, where t runs from 0 to 1. All right, so if we simplify it a bit, that's 3 minus 2t, comma 0, comma 1, with derivative negative 2, 0, 0. Okay. And game, we can now apply your definition of the line integral to compute the work done. Notice now, we are considering the line integral along C1, not along C. Here, it will not matter because we noted that this line integral is independent of path. Okay? So let's expand this thing a bit. It will be the integral from 0 to 1 of f of R1. R1 is 3 minus 2t, 0, and then 1. Okay? And then dot with R1 prime. So when we do the plugging in, the first component will look like this. The second component will be, well, ang y kanina ay 0 lang, so 0 yan. And then for the third component, it will be this one. Okay. We will be taking its dot product now with this one, R1 prime. So, yeah, so once we set this up, at this point, algebra na lang ito plus remembering your antiderivatives, no? All right, so that will be the result. Here, a bit of substitution may help, no? We let u be 4t squared minus 12t plus 10, so that du is 8t minus 12. And, 4t minus 6, that's 1/2 of this. So, it will be reflected later. First, let's change the bounds for t to bounds for u. They will be from 10 to 2. Okay? And then we have the function now, 1 over u, and then 1/2 du. And then the rest, hopefully I could do some line jumping here and show you the final answer, which coincides with the one we obtained from solution 1. Okay? So that will be the work done by F along this curve by way of considering the line integral along C1. All right? And that's it for your fundamental theorem of line integrals and independence of path. So if you have more items that you want to try, you may try the items from the module if you have it, or online resources if we could give you some, okay? So that's it. Thank you very much for watching and stay safe.